Okay, very good morning, everyone. My name is Tamoghna, and today I will be explaining to you Explainable AI. So for the agenda for today, I will be having major understanding first, clearing out the terminology of interpretable and explainable, uh, the basic concept of SHAP, where we are currently with it. How is line different from SHAP in a very brief way? And also, since I've been working on the NLP side, I will be explaining tabular-based SHAP informations and stuff. But apart from that, I'll also give you a small idea about how SHAP works on an NLP basis. And finally, which one should we use at the end of the day? Now, if we have to look into the terminology differences, it's pretty much interchangeable. However, just on a basis of time and mechanism, interpretable and explainable terminologies can be used. So, in terms of interpretable, it's a kind of a priori where we can obtain the knowledge of a output or the outcome of a model based on the concept that we are analyzing. Whereas explainable is kind of like knowledge that we obtain through observation and experience, kind of like having a SME for a particular topic, and then based on that we will be able to explain it. But sometimes if those informations are not available to us, then interpretation will be useful in those situations. Sometimes what happens is that in interpretable, we are able to understand the summaries of the calculations, that why a particular output happened, and we can get some conclusion and some specific idea. Whereas explainable is kind of like a surrogacy, where we need another model to create a hypothesis of the mechanism, like why a particular situation has happened with us. And based on that, we will be able to explain the result. So we need some kind of a support model to explain the outcome of the original model that we are experiencing or going to use. And finally, we can, when it comes to interpretable, we have those tabular records and data, so we can pass along some specific input parameters and get the necessary tweaks and changes to get the desired outcomes. So we can recreate it to some extent. Whereas when it comes to explainable section, we might not be necessarily have the ability to rebuild by hand deterministically. So these are like some very high level differences between them, although it's like they are two sides of the same coin. But there is some a little bit of terminology exchanges that happens, which kind of gives us an idea that why these two should be used in a very cautiously. But the main question or the agenda for us, of course, is to move the focus whenever the model interpretation that we do is to move from what was the conclusion to why was this conclusion, right? That's where explainable AI comes into picture. And of course, why is it important to us? First of all, fairness. We must be ensuring that the model outcome is fair and there is no biasness in the information. Secondly, the reliability. We must ensure that the model outcome that's getting generated is reliable enough to be deployed in the production to ensure steady business outcomes happens in the way we have expected. And finally, causality, to ensure all the dependencies are interrelated with each other and we can provide some causation of the outcome of the model, that it makes sense logically as well as technically when it comes to providing a solution to the ML world, right? I'll come to this causality part a little bit in the end, but let's move on to understand better on the remaining sections. So how do we interpret the machine learning models? We can split it up into two perspectives. One is the category, where we can move on a model specific or model agnostic, which means any model. Model agnostic means any model, and model specific like specific to XGBoost, tree forest, or those kind of stuff. And then the other one would be in terms of the scope. So is it going to be a local scope or global scope? Local as in like each individual records we are able to explain, or global like on an average for all the possible values that you have, can you explain the impact of the independent features on the outcome of the model? So mainly this is what the entire paradigm of explainable AI is. Now let's go on to the actual topic of today's session, which is SHAP. So SHAP is basically Shapley additive explanations. Let us come to the part that where did this idea came from. So this part Shapley that you're looking into, it is derived or it's being used from the cooperative game theory. So in the game theory, there is this concept where if you have a coalition C, by coalition we means interaction between individuals. So if you have a coalition and in that coalition you are expecting a outcome V, then how can you tell that which particular individual provided how much to the value? Like how much has individually contributed to the overall outcome? So since we are talking about game theory, so let's consider Kaggle competition. Okay, so four team members are formed. Each one of them has their own specialty, and maybe one of them is like just for the namesake they are there. That every person in that project who has no idea what's going on. So something like that, if we can consider where they are in that game, and of course the prize, the outcome of that game would be getting a prize money, depending upon if you get a position in the top 5 or top 3. So what should be the fair distribution? How do we determine it? Right? Now, keep this thing in mind. Replace the individual participants as your features, as in column 1, column 2, column 3, column 4. Replace the game with ML black box model that you have, XGBoost, random forest, linear regression, PyTorch, deep learning, NNN, whatever. And price would be the predictions. So keeping this entire part as my source of problem, the solution is going to be the Shapley values. So Shapley value will help you to determine that which feature has provided maximum contribution to the final outcome of a model, right? So one important thing, so SHAP, this is like the icon of the official SHAP GitHub repo, where the two authors who provided or published the paper back in 2017, they derived this Shapley concept from this cooperative game theory and implemented it in the machine learning models to explain what is the contribution of each feature to the final outcome of a model, or the predicted outcome of a model, right? Now, the main thing about SHAP is that it is always going to be a local scope. So you are going to do it on an individual record level, but it can be expanded to a global scope, right? Now, let's get a more detailed understanding of how this entire thing is happening. The main intuition for us, the coalition that I was talking about, right? So how the coalition will work with and without a specific feature. So for an example, among these core team members who are participating, let us consider that this guy is ruled out from the competition for some reason. And it turns out that he is the subject matter expert. So without his guidance, that causality part or the business impact part will not be more implemented. I mean, it will not be making much of a difference. So the kind of feature engineering that you should be technically doing, maybe you are not going to get to that proper result state. Now in the competition, you know that the first position people will get $1,000 and the second position suppose will get $700. So consider that after removing that fourth person from your competition, you end up getting the second prize. So from this information, these two data, you will be able to comprehend that the valuation of that fourth person is $300, because without him, you would not have won the competition. So consider you have won the first, you got a first position because all four of you were together. But now suppose you discarded him and you got second position. So that valuation for that fourth person is $300. So that way you can determine that, okay, so this is the contribution of a feature 4 in the final outcome of my model. However, it's not that easy. We need to also consider the interactions between the features. Let's say the third person has a huge ego and she is not reluctant to cooperate or collaborate with anyone, and she would like to do everything in the way she is doing. So of course there will be some clash and conflict, right? So how do you manage and ensure that you can get these things working properly and ensure all the possible permutations are performed? before you, or I mean, not permutation, all the possible combinations are performed before you get the final generalized solution. So what we do, we will be taking pairs. Okay, so all of these pairs of features will be considered as a part of our process, where we can determine, okay, that these set of so what is the outcome when we ignore a particular feature or we ignore a set of features, then what is the outcome. Okay, so that's where this entire contribution of an individual feature comes into picture. And that special, I will come to this picture later, and that special terminology is called marginal contribution. So, as I was mentioning, the coalition will result in a value. So, think of that value as the price, right? So, value with all the four members and value with only the first three members. So, how will you determine the marginal contribution of the fourth member? Simple. You just subtract the value of that all of them minus the one without that particular individual. Just like we did 1000 minus 700. So 300 would be the marginal contribution of the fourth member, comprising of the team members having only the 1, 2, and 3. So similarly, you will be getting a lot of these combinations of having only one. So suppose you are keeping the fourth out of the equation, but you're also keeping three out of the equation. So that way you will be getting a lot of these options or a lot of these combinations where the fourth member will not be present. So fourth alone is not present. 4 plus 3 is not present. So technically 4 is also not present. 4 plus 3 plus 2 second member is also not present, so hence technically 4 is also not present. So in this way you will be getting all the possible marginal contributions. You're going to take the mean of them, and that is what the Shapley value or the feature attribution of that particular model is what you will be getting. Okay, so when we are talking about coalitions, right? So what happens in coalition is that we try to map a binary or a discrete distribution of all the features against the actual feature value that we have. So if you see in this, let me turn on the laser over here. Okay, yeah, my bad. So over here you can see this correlation, right? So this correlation is basically holding binarized one value, which means all of these features are currently present. So like all the four members are present, and that is basically mapped with its corresponding feature values. So when we say that we are going to skip a particular feature or ignore a particular column, we just cannot simply eradicate that column, because we know that in machine learning, whenever we pass a variable or a set of features, that feature size has to be constant whenever we are going to do any kind of feature ignorance or anything like that. So we just cannot vary the feature size, right? Otherwise we'll not be getting a steady model out of it. So what do we do in that situation? What we are supposed to do is that we're going to fill those um, skipped out features with some random values. How are we going to get those random values? I'll come to that in the next slide. But technically, if you are going to skip, suppose weight and color as a combination, just only keep the age fixed. Then age is the one, remaining are 0. And of course, these 20 and blue that you initially had, that will not be same anymore. And we will be replacing them with some random values. Now, how are we going to get those random values? I'll tell you in the next slide. Any questions till this point? And if you have, please start writing it in the comment section so that I can address it once the session is done. So let's now understand the basics of SHAPs. As I was mentioning, like it's Shapley additive explanation, right? So Shapley you understood from the game theory perspective, and explanation you're also understanding by the term itself. So what is this additive thing coming into picture all of a sudden? So this is what makes it different from line. I'll explain to you as I go further into this one. So what happens is that suppose you have original instance, okay, like a particular value x, and fx is the corresponding model prediction. What happens is that you are going to take a simplified input over here. By simplified input, I'll explain to you what exactly we are referring to. In the previous slide, if you saw that we are replacing age, like the color and some other thing with some another value, right? So so that particular thing becomes a simplified input. Simplified input in the sense like this is the subset of the original data set that you are taking it as an approximation to say that the explanation model, which is g of x, is also going to be identical. So if you take the original x and you try to get a simplified approximation by randomizing some of those columns, then the function that you're going to get out of that simplified output is also going to be somewhat similar to what the actual model will be presenting to you. I'll explain this as we go further along. And that is basically called the local accuracy, one feature of the additive functionality. So this explanatory model is basically phi of 0 called null effect plus summation of all the Shapley values corresponding to the simplified input that we have. So just think about it as a single row of record where you're just randomly replacing some of the columns, and their corresponding Shapley value is going to be phi I. So the summation of all those phi I along with those x values plus the null effect, which is going to be the expected outcome of the model or the base value of the model, that basically forms you the additive feature contribution. So this is where the additive functionality comes into picture. It's a little hard to follow in the beginning, but once you read up their actual SHAP uh, documentations that they have it explained it extremely well. So I will highly recommend you to also read up the documentations from the SHAP because they have provided a lot of information about that. So that goes one feature. Like there are three particular informations where first we can say is local accuracy. The second one is called missingness, which states that if a feature is missing, then the Shapley value contribution is also going to be zero. We cannot just have any kind of negative positive value corresponding to that part. So that's basically what we get in terms of missingness. And the last one is consistency. So consistency tells us that if a feature contribution changes, then the feature effect cannot change in the opposite direction. So if a particular value of x or a column changes in the original model, then in the explanatory model, it cannot go in the negative direction. If it increases in the actual model, in the explanatory model also, it should also increase. Okay, so this is what the additive functionality represents in the SHAP perspective. And so the authors of the SHAP paper have explained that LIME as a interpretability tool only supports local accuracy. These other two informations gets missed out. And this overall includes the explanatory function a little bit more accurate. And that's why SHAP is relatively better in terms of the LIME counterpart. All right. Now, so this is actually the equation associated with the SHAP value. So I don't want to scare you guys and go all details into this part, but mainly the objective is to calculate the corresponding phi value over here, where we can say that f is the black box model and this is the data point input followed by the weighting part. So what is this weighting do? It provides the weightage of the contributions of each of the features. And AM is basically the total number of features. So 40, whatever you have, that is basically what we get over here. And simplified input basically is referring to those randomized sections that I was talking about, right? So what happens is over here, this weighted score is getting calculated in the form just like the NCM kind of a thing, and this provides the weightage associated with that particular subset of record, provided a particular feature is skipped. So with and without that particular column, all of this will be present over here. So as I was mentioning about those subset or simplified records, this is where you can pass along some random value to any particular column, like age is 36, so randomly you can pass along 6 or 12, whatever, etc. And with that, you will be getting some simplified input for the explanation of the model. So why are we randomizing it? So that the model can understand all the possible scenarios that it might encounter also in the future, so that it can still have a generic understanding of how to explain the model at the end of the day. Like unlike there is going to be a drastic change in the features for some kind of reason, just like how COVID hit us. So at that point of time, everything spiked dramatically overnight, right? In 2 days or 3 days. So model will not be able to function properly in those kind of exceptional scenarios. But for the normal scenarios, in order to obtain that steady outcome and get a generic explanation throughout, that is where this randomized factor comes into picture to give us a better score. And as I was telling you that if I had some m number of features of columns, I will be basically taking and removing some of the features at a time, but a combination of features also, right? So if we are planning to eliminate, if we are having these 10 features altogether present with us, then total number of combinations of features present and not present is going to be 1024, like 2 to the power of 10, right? Considering we eliminate only two features at a time, so all of this can bring us about these many possible combinations. And of course, if you imagine we have 40 or something, then we will be ending up with millions of uh, permutations and combinations associated with Shapley value computation. So it will become extremely time consuming, right? So the complexity of the Shapley is basically 2 to the power n possible subsets of set. So if you're just taking whatever the number of features are there, so that many possible combinations of subsets will get created, and the complexity or the calculation of the Shapley value will become too expensive for us if we have too many features, right? In order to handle this particular solution or this problem, the solution is basically Shapley kernel. So now what happens is Shapley kernel. So it's actually a very detailed mathematical part. So if you want to know more details, just a early suggestion that you can read up the paper, but I just try to provide it in as easy way as possible. I don't want to bore you guys. So think of a SAP sample of a records that you have taken, where any one particular feature is getting missed out, okay? And you're getting the corresponding ground truth, what is going to be the ground truth output associated with it. So what happens is that as we skip or remove part of the feature or any one particular feature, we're going to fill those out with those random values, right? And these random values are called background data set. So how do we get this background data set? It is from those original training data set itself, where you randomly take some samples like 100 or 1000 depending upon how big your data set is, and using that you are going to replace the original value and replace it with those sample values that you are present with the background data set. Of course, you will be replacing only with the corresponding value and nothing else. I mean, with the corresponding column and not anything different. But mainly, we are going to keep those other features fixed, the value, whatever they have, and we're going to just fluctuate the one which is not present. And in this way, we are going to get all the possible predicted value. And do once we get all of those possible combinations, we'll take an average of them and we get an average predictions out of it. So what happens is that the objective is to perform a weighted linear regression model, where the objective is to find out the coefficients associated with this feature having this target output or expected target output. And how do we adjust these or provide weightage to these individual outputs is through these weight scores. And how these weight scores are calculated? The weight scores are calculated based on this particular formula. So total number of features minus 1 divided by m combination of c, like how many features are included in this particular instance. Okay, so m is suppose 5, total 5 features, so 5 minus 1 divided by 5c 2. Suppose we have included 2 features in that particular set, okay, and remaining are there. So 5c2 multiplied by number of features included in that c, which is 2, times number of features excluded in the c, which is 3. So that way you are going to calculate the weighted score for each of these weighted expected output. And based on this, there is some fundamental calculations happening in the back end, which will eventually help us to give our desired approximate Shapley values. So instead of going into that extreme computational details, where you are going to consider each and every combinations of those informations that you have left with, that you have with you previously, you are going to use this approximation value to get the final outcome at the end of the day. So weighted linear regression that you see over here is basically the kernel SHAP, which is the most widely used explainer, SHAP explainer for any model that we can leverage. So it's a model agnostic SHAP explainer model that you can leverage to understand which feature has the most importance or the outcome at the end of the day. So there are other versions of SHAP, which is called deep SHAP, linear SHAP, tree SHAP. So deep SHAP, as you can understand, is specific for deep learning based functionalities. Linear SHAP is for linear regressions model. Tree SHAP is for random forest, XGBoost trees, and all of those parts. So this becomes again model agnostic, model specific. So kernel SHAP in general is kind of like a model agnostic that can help you to get some different results. So as I was mentioning that how is Lime different, which is called local interpretable model agnostic explanation. So you are pretty well understanding the terminology. It's pretty much self-explanatory itself, right? So it's only local. You cannot scale it up and generalize it to a global scale. So that is one major difference. And because of this only, as you remember, when I was talking about additive part, only that local accuracy is getting justified and nothing else. So if you think of a very complex model where you are basically trying to say if a particular individual is eligible for a loan or not, right? Then suppose these are the two features and this is kind of like the complex model curvatures of the fitted curve, for example, just giving a rough idea. And this is where all these some samples of records of data are distributed. Now you have you have said that John Doe is not eligible for loan, then you must be held accountable that okay, tell me why am I not eligible, right? So what do we do is that we try to go localized into that particular individual section, and then after zooming in, this is how you can see the where, so this pink center is basically corresponding to this particular person, John Doe, whatever. And from here we are going to perform and create a linear regression model to see that okay, how much is that delta happening, for which I'm able to say that for which I'm able to say confidently that he is not eligible to become to be approved of the loan that we are providing. So in this section, again, the formula is pretty much similar to where Shapley uses. And basically over here, this is that approximation of that model, just like how we are approximating in Shapley by taking that weighted linear regression part. And then there is some additional delta functions or a sigmoid score, which says that we should be keeping this explanation or the fitted curve as simple as possible. That's a pretty huge math, so I don't want to go into that part more. But how are we training this linear regression model to explain or justify that you are not eligible for this part? So you basically take the center and start populating randomly these subset of records randomly, and then you start to take some concentric circles of heat map that says that okay, within this area of region, this kind of model explains to me that I'm getting the least possible error. Like ultimately, the goal is to ensure that the error is the least, which explains that the or the R square value is probably high. That justifies my statement that the independent features are explaining the final outcome of the model. So there is some levels of mathematical computations going on in the backend, which states that you are going to randomly feed up this section, and then you're going to train the model, and from that fitted outcome, you're going to confirm the proof that this model is actually not able to that you are actually falling under that category of loan approval, and those features like feature 1, feature 5, feature 15, whatever the features are present, these are the features that are actually supporting the fact that you are not eligible for loan. But again, this is where the only local accuracy part is coming into picture, and no other missingness or consistency. None of these are actually going to be useful for us. So imagine if you set the random seed differently, you will be generating a different sets of information. However, the best thing about where the Lime operates is that there is not going to be enough skewness or deviations from the one result to another. Okay, so internally, they have provided that level of functionality to ensure we get consistently or somewhat similar outcome. But there is no guarantee, as I was mentioning, because once you change the seed, you might be getting a completely different explanation. Like the feature 1, 5, and 7, which were originally contributing for the final outcome, you end up getting maybe feature 1, 5, and 8. So something like this kind of inconsistency happens with Lime, which is why sometimes it's not recommended. Now, before jumping on to any other things, we know that in NLP we have multiple use cases and translation, chatbot, sentiment analysis, search engines, summarization, fake news. So sentiment analysis, I think, is one of the most easiest things that we all do. And over here, we can just quickly explain to you how exactly NLP in this SHAP way works. So think of, and whenever it's in NLP, we always know it's going to be in terms of tokens, in terms of like whichever the smallest possible chunks of words that is a meaningful for the model to understand, right? So depending upon various tokenizers, you use Roberta, you use Distilbird, you use Bird, anything, depending on that, you will be getting different tokens of information. Using those token informations, what we can do is with that we can pass along the transformers pipeline, which by calling sentiment analysis classifier, and then perform the necessary SHAP explanation at the backend. And in that explanation, I'll just quickly tell you what happens. Over here, what we do, we end up getting the predictions for the logits or the classes that we are actually available with. So if you have a positive and a negative class, then we are going to get those corresponding to values that are going to be present with us. And then we are going to pass it along through the Shapley visualization plots examples that we have, condensed plots, force plot, text plots, etc. And in that section, what we get is something like this. So f of x is basically kind of like the expected function or the expected output of the Shapley values that you are going to get. So previously in this, I just took a screenshot from the Shapley documentation. At present, you're actually going to see the way you are going to adjust the scores of the value. Okay, like if it is between 0 to 1, you're going to get that f of x in that range of 0 to 1, like 99% confidence score that it's a positive. So 0.99 will be something like that you're going to get in the outcome. So what happens in terms of the color notation, the positive red, so this is kind of called a condensed plot or force plot. So it tells you that whatever the red values are there, it's kind of pushing towards the higher output of the model, whereas the blue ones are pulling it away from the expected value or the higher outcome of the model, right? And in terms of sentiment analysis context, the red means it's more positive review, whereas blue means it's more negative review. Okay, so this is how, in general, this particular pattern works. So this kind of gives you the extension of which that how much of a Shapley value contribution has been provided, and as you can see, there are even though the proportion of the rate scores are pretty low. I mean, the number of characters, number of tokens, that impact is much higher because here you can see based on the colors scored, right? And whereas blue has a little impact to make it as a negative. In the end, what happens is that we also try to do how internally it actually operates is the way they try to club together all of this textual information or a token information in terms of the impact it is creating, right? If it's a positive, then which all hierarchical informations are being considered together to make that final outcome as a positive. So these importance values of each of these sub chunks of words are basically hierarchical in nature, and they have some kind of nonlinear effect between them, and whichever has the highest level of nonlinearity, they get auto-merged together. That you can see like Randall with such, professional, ism. So this is like how the Roberta tokenizer works, right? So professionalism was the actual terminology, but after doing tokenization, it got split it up and it got present in this particular format. So in this way, these particular chunks of informations, which finally forms together that overall big chunk of red text that gets provided in this hierarchical information format. And in this way, you will be getting whichever columns or informations are providing the final outcome altogether to get the final result. Okay, so this is why this clustering, hierarchical clustering diagram is essential for us to understand that, okay, which part worked out well in this particular format. All right. And finally, we have SHAP in CV, Lime in NLP, and there is something called as trans SHAP. So nothing technical over here. I'll just show you what is happening. So in Lime over here also, if you have a positive sentiment analysis model, similarly, just like how we have shown in that bar plot, here we are actually also showing that which parts are contributing more negatively and then which part is contributing more to the positive side. But again, without much of a context on the only on the local accuracy perspective and not on a global perspective. Then there is something, another paper got published last year, which is called TransShap. that tells you it's kind of like an amalgamation or a blend of a lime and a SHAP, and tells you that exactly how transformer specific architecture models are actually providing the explanatory outcome of a particular prediction. Like for here again, it's a sentiment analysis. Here, as you can see, it's the output is pretty much similar to the way how Lime operates, but internally they showcases it in terms of SHAP. So SHAP functionality is more predominant in the trans-SHAP section, and they have fine-tuned it for transformers-based architecture to ensure they get more reliable and accurate result. So this becomes a model-specific global or a local model of the SHAP part. So that is specific to transformers. And similarly, in computer vision, we can see that we have 2104 as the ground truth images. So for various kernels or kernel maps that we have, which particular kernel map is actually responsible to provide the most information present to mark it as a prediction as 2 or 4, right? So what do we have? We have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we had those 9 numbers present with us, right? So the kernel that we are going to finally have at the end, the kernel map, in which of these number locations has the highest impact or significance, right? So that's why you can see like it's underneath it's 0, so it's not a match. Underneath it's 1, but here you can see slightly negative blue because in 1 you can also get some kind of arrow mark like this. But here in 2, as you can see, where most of the heat map or the contribution, this is where the kernel understands that yeah, there is more similarity of overlap of these two with the ground truth 2 that we have with us. Similarly, it goes for 1. Similarly, it goes for 0. In 4, as you can see, in 4 here, the heat map or the red map contribution is positively providing it to all the 4, 1, 2, 3 sides and also on the top. So logically, it would have given us 9 instead of a 4. However, when it came to the ninth digit or the ninth number, here you can see the blue color got kicked into the picture, which nullified this red, and we got this blue part over here, making and only providing us remaining with this part, and this part, like the left, bottom, and the right side. The top part got eliminated. So this is how also in computer vision this particular operation works. Now to quickly wrap up on which one should we use and why should we use this, right? So what happens is that in practice, a model agnostic implementation of the SHAP, which is the kernel explainer that I just showed you, or the kernel SHAP, is slow even with approximation, whereas tree SHAP is 100 times faster. But again, it becomes model specific. So there is a trade-off, and you need to take the call that what you want to go ahead with. Lime is not designed to work with one-hot encoded data. So if we are passing along a data set where we have these character representations and we are making it as a one-hot code format, then Lime fails to operate properly in that local accuracy perspective, and you will be ending up getting incorrect results. So in some cases, the local model built by the Lime may fail to approximate the behavior of the model. As I was explaining in the Lime slide, depending upon the random seeds, you will be ending up getting different random dataset generation to justify the final model outcome. So that approximation of that model might not be exactly similar, and it will vary. So it's likely to vary. SHAP depends on the background dataset to infer a baseline or the expected value. So that baseline or the background dataset that I was talking about, where we are keeping some of the features fixed but fluctuating that one particular column value. So depending upon that background dataset creation, it also becomes very computationally expensive if it's a huge dataset, like millions of records. So even if you take a sample which has like 10,000 of rows, then it still becomes extremely computationally heavy. So in the end, it's ultimately going to be a trade-off on the accuracy or the speed of execution. So it's going to be your call. Shapley value decomposes the final predictions into the contributions of each attribute. This is what some mean by consistent, and it is not something that you get from Lime. As I was again telling you in that same perspective, the randomizations sometimes are present in both SHAP and Lime. However, in Lime, that level of randomness has a much more impact compared to what SHAP provides. So even if you restart your server and set up a something different seed, you will not be getting a way too different outcome from a SHAP value. Whereas you will be getting somewhat good difference when it comes to line. So that is how you can justify the outcome of the models. SHAP also provides more visual explanations. If you go through the SHAP documents, you will be seeing like waterfall chart, bee swarm chart, force spot chart. Lot of them are there, so that can explain and give you scatter plot charts are there, everything. So you will be getting a huge amount of idea on how to visualize this information. And lastly, of course, Lime is inherently local, whereas SHAP you can give us or you can get global interpretations of the model. And for more details, you can definitely visit this interpretable ML book. It's an extremely well book. So here you will be getting all those mathematical details explained that you is which is present in the original paper. So if some of the parts of the PPT you have not understood, then you can definitely check out this link. And here, from here, just type interpretable ML book also. You will be able to get the first link itself. So I'm done with this section, but I'll just quickly show you just the notebook in 10 minutes or so. So over here, what we have is some explanations of the SHAP in terms of the regular data that we use, or tabular record, and how do we eventually move on to this part. So that base value, expected value, how is all of this working? I'll just quickly walk you through in this example. So basically, we are taking here a Boston data set, and in this Boston data set, we know that it's like ultimately predicting the price of a property in Boston depending upon few features like age of the property, crime rate area, all of those extra informations that you can think of, right? So in this section, what we are going to do, we are going to quickly check some functionality and how we are reaching to that particular section. So the mean value of the median house price in thousands of dollars is 22,000 something dollars. So over here, once we take up subsample trains and everything, what we are doing is first let's try to do simple linear regression model on this one. What we are using is over here we are using something called as sklearn pandas. So sklearn pandas is kind of like a simple wrapper function which can help us to perform all the levels of pre-processing, be it like imputation or scaling. All of those parts can be performed in this simple function, and you can map it easily. So all the categorical columns are getting ordinal encoder, and all the numerical columns are getting a simple imputer with a strategy median. So if you have a missing value present in that column, you will be replacing it with a median value, and then you will be performing standard scalar. So stuff like this is what we are able to do, and using data frame mapper, we can get that part properly. So in this way, we are going to train a linear regression model using a stats model, and here we are just going to run some few evaluations. Here we are seeing that the mean absolute error is 4.73. And as we, so here in stats model, once we do a result like sm.ols, and then we have a summary. So in this summary, it tells us again more detailed information about the model outcome as well as the coefficients that we are present with it. So whichever has like the highest coefficient values, we can say those are the ones that usually contributes to the output of the model. However, it's not always going to be exactly that same logic over and over again. What I mean by this over here, that suppose we are considering the age, right? So age has a coefficient of 0.0838. Now this age is in terms of numbers. So if we just change the value of the scale of that number from years to minutes, then you're just going to multiply this coefficient with 365 into 24 into 60. So you'll be ending up getting like a huge coefficient value, so which is not relevant for our problem statement. Now, our general idea when we just read about Boston house pricing, it automatically comes into your mind that yeah, we should be judging the property by the on the basis of a maximum month, otherwise years. But since we cannot just go to the level of minute just to get or make sure that that feature has the most importance throughout every possible scenario, that is kind of like a biasness, and we should not be incorporating it. So that's why the scale of the feature is extremely important to determine the coefficient. And that's why coefficient alone is not at all responsible for providing the final outcome of the model. So you need to be very careful and you need to understand the features. That's why understanding the features are extremely important before providing some suggestions. So that is one way. And again, now we have a random forest operation where we have another set of test records. And again, here we have internally specific to random forest regressor some feature importance. And when we run the feature importance over here, we are again getting RM, L stats as the most contributed outcome over here. Similarly, in neural network, if you run it on a simple PyTorch record, you just train the model, but you are going to get some kind of loss and something. However, internally for PyTorch or anything else, there is no that variable VIF kind of stuff or stuff like this are not present internally in PyTorch. So you will not be able to justify and tell that which feature got most important out of it. So to handle all of this, all these are all model specific explanations and all. So to combat this part, that is where SHAP came into picture, right? Now, just to get that intuition of this part, that how are we going to make that SHAP part work. So similarly, just like how in that linear regression model that we were using, let's go ahead with that part. So for the numerical column, we had the similar implementation, simple imputer with strategy median, replacing null values with median, and then performing standard scalar. Here for the categorical column, we're making a small change. We are going to impute missing values of categorical columns with the value 0. Okay, and then we are going to do an ordinal encoder just for scaling purpose. So once we run this record, we get a pipeline ready with us. Now, what we are going to do right now is going to pass along a inane data frame. So whatever this inane data frame is, basically we are going to have all the columns with all the values as ANN. Now internally, when we pass this to this pipeline function, it's going to get first processed into the mapper function. So as I was mentioned, like if you have a median value, if you have a NaN for numerical columns, it's going to address that particular column's median value and replace that NaN value with the median. And if it is a character based, it's going to fill it with a 0 constant. So that's why when you pass this NaN data frame record to a mapper function, you'll end up getting the corresponding median values out of it. And now when you pass this transformed record into the pipeline, where you are basically performing the linear regression of this particular data set, and then you're going to do a prediction out of it, you are going to get the base value, which is the expected value of the model. So whenever you do not have any value present in that particular record and you have already fitted your model, then what is that base value that you're going to get out of it? And this is how you calculate the base value, which is this F line that I was talking about. Uh, this this is the base value that you can see in this section, right? So this is that base value that gets calculated roughly. It's not exactly this particular mathematics, but roughly. Now, so now if we take up any particular test record, the first test record, and then we perform pipeline prediction on top of it, we see that the current prediction from the model is 5.887, whereas the actual value is 8.58, right? So we know that the base value of the model is 24.392, and what we are getting as a prediction is 5.87. Now, how do we justify that for this particular record of the test set, we are going away from 24 to 5.87? So which feature has contributed so negatively to our particular record that we have seen over here, this 0th record of the test column, that we have pulled down our from our base value to this value? So base value is basically like the expected outcome. When nothing happens, this is what you will going to get. So even if no one participates in the competition, if someone admits or submits something, you will still get a rank. So think of it something like that. So that is the base value. So this is what we are supposed to find out. Now, the very first approach that we can think of related to Shapley values is called partial dependence plot. Now, in the partial dependence plot, what happens is that for each of these particular features that you are present with them, it's going to tell you that how much is that difference from the expected value of the final outcome of the model to the expected value of that particular feature column that you have present with it. So I'll just explain it over here very quickly. And finally, in this section, in this partial dependency plot, what happens? So right now, the SHAP explainer is performing that explanation there. So we got the G of X, that explanatory model ready with us. So once we plot this particular partial dependence plot, here we can see this horizontal line as the expected predicted value of the model. Okay, and this is like the expected mean value of the particular column that we are observing. So this light gray colored curve or this distribution that you can see is the histogram of that feature. So this blue line that you can see is basically all the partial dependency plots that you can think of, or basically all the Shapley values of each of these individual records that you have with you. And if you notice that it's exactly intersecting this expected value of this particular column against the expected value of the model outcome. So similarly, across all the other possible uh, features that you can think of, you will be seeing that exactly similar functionality and feature. So expected value of this radial function and the expected outcome of the model, provided that we are passing along the radial function itself. And this red colored line, vertical line that you can see, this is basically that Shapley value. So Shapley value is the difference between the expected value of a model minus the partial dependence plot corresponding to that particular feature that you have selected. And this red line that you can see is only for a single value. Now, if you do not perform partial dependency plot like this, if you just do a scatter plot of all of these Shapley values, you'll be getting this vertical line itself. And that is where exactly this partial dependence plot basically tells you in a very one by one for each record, for each column, how exactly the contribution is happening. But of course, it becomes very cumbersome and it becomes very difficult to visualize all of these informations all together. And that is where now all of those fancy charts comes into picture, waterfall chart. So here, as you can see, you will see the expected value of the model is 23.904, right? So, and what we had calculated over here was 24 point something, right? So there is some delta trade-off in the calculations of the Shapley values, so which makes this more accurate. And here you can see that for each of those possible features that you got, which one contributed negatively, which one positively. So this crim as a variable have contributed most negatively and then followed by LSTAT, for which your final expected value got 5.887, which is what we got also over here, right? 5.887. So likewise, you just have to explore all of these plots and understand the fundamental differences between them to see that why exactly my prediction outcome is obtaining in this way and why is it getting deviated so far away from the base value. So this is for the first corresponding zeroth record. This is for the second record. Here you can see the difference in the prediction of the outcome. And here LSTAT contributed most negatively, whereas here RM contributed most negatively, followed by LSTAT. So this is where how the information gets passed along, and you will be able to make some idea and get some sense out. And then similarly for the overall model, if you have to get a global understanding of those individual models, you will be able to pass along it in this way, shap.plots.bar, and then this is going to be the global level informations that which of the features have most contributions towards the outcome of the model. Similarly, so for linear regression model, you've got something like this, and summary plot is also present over here. And then similarly, you can perform it also for the this in NNN transformers models and every other details that you can think of. And then finally, here in this section, what we are doing over here in SHAP in NLP, so we are calling in transformers model. We are loading the Distilbert uncased model for performing the sentiment analysis, whatever we have. So this is the base tokenizer and the base model for us. And once we loaded this model, we are performing a tokenization. So Distilbert has this level of tokenization. Roboter has something different. Then what we are doing is we are calling the transformers pipeline, and we are calling the sentiment analysis task over here by defining the model and the tokenizers and every other details. Then finally, what we are doing is that we are loading the IMDb dataset from the datasets of Hugging Face. And from here, what we are basically doing is that we are calling up a particular text to see what is the sentiment of that particular model. And as I was mentioning, positive, the dark pink shades more means more positive contribution, whereas the blue indicates more negative contribution. So this is like for all the individual tokens, how much is positive value, how much is negative value contributing. Okay, so in this, and if you notice, they are just swapping in terms of the negative signs. More or less, that's what the overall contribution differences are between them. And finally, once you do a force plot out of it, you will be able to see that, okay, better even if which one of these particular tokens are contributing most towards the negative. Um, Here, see, so boring has the highest uh, uh, score and weightage. Blasphemous has the next possible things. So all of these parts are providing you a much better insight and clarity. However, also just to keep one thing in mind in general, that SHAP, you should not be blindly trusting SHAP, because you need to also understand the it does not explain causality. So that's where I was talking about the causality part over here, right? So in causality, what is happening is that your business model is saying that if a customer is supposed to retain the customer retention, okay, or customer churn. So you have a subscription where it's like a suppose Amazon Prime. So how will I ensure that a customer is going to retain, or he will be renewing the subscription, right? So what will happen in those situations is that you narrow down to three features that says that, okay, number of discounts provided, the number of bugs reported, and gender. Okay, so something like these three features came out top from the SHAP outcome. So you decided, okay, so the discounts that I'm providing are providing the most impact, so let's provide discount to people as much as possible to retain subscription and membership. But upon further inspection, you realize that it's actually the people who reports more bug is the one that is returning the most from a business analyst point of view. But how will you justify this? So here you can say that because these people are actually actively reporting the bugs, that means that this individual is interested in our platform more. So there is a chance that if we respond to those individuals, they will understand that they are being valued, and hence they will have the scope to retain more rather than the people who have been bombarding it with discounts and coupons and stuff like that. So that is where causality comes into picture. So the correlation does not always justifies causation. We know this thing, right? So causation is something that is equally important for us to analyze. So we should not be blindly trusting what SHAP provides us. We must be aware of what the statistical significance as well as the business significance for those features that we are considering. Is it going to be useful in the end to make the final judge call or not? And with that you will be able to get a much better insights into the models. And I will definitely recommend you to read the SHAP docs, the documentation of the SHAP. They have a lot of details, lot of explanations, and you will be also getting an idea about fairness of the model, that the biasness part that I was talking about. So all of those things have been mentioned very detailed in that SHAP documentation, so you can definitely go through that part. And with that, I'm done with the presentation. It took 1 hour. Sorry. So any questions?
Yeah, we can take questions. So whoever having questions, you can unmute and ask the questions. There are some questions. So slides, yes, I can get from Tamoghna and upload it and share the link. I can share it over email as well. And session, yes, the recording I'll upload later in the YouTube and share the link in the same event page comment section. So anybody having any questions? Please unmute and ask
Hello,
the question.
hello, Tamoghna. Am I audible?
Yeah, yeah,
Yes. So, amazing presentation. It was a very good presentation. But I have one small doubt.
yeah.
So, can we extend SHAP to understand instance segmentation models?
Uh, Instance segmentation. Can you explain?
What like you showed for the classification models, right? The
Uh-huh.
MNIST. And in classification models, it's only we have a single neuron outside. We just predict whether it is what kind of class. For binary classification, it's single, but for MNIST, there will be 10 different classes,
Correct.
right?
Yeah.
But for instance segmentation, there will be for every class, there will also be regression associated with it, which will incorporate the bounding box.
Hmm.
So, so it's like one very basic example is person detection. If we
Uh-huh.
give if we give an image, we will get like if there are three people inside the image, we will
Uh-huh.
get three people bounding boxes and also their classes that these are person.
Hmm.
Yes.
Okay. Okay. I think
So
Yeah, I think that might be possible. I have not actively done a hands-on on the SHAP on the CV side. But yeah, I think Deep Lift is one model or a, I think, framework which explains this particular section for object detection by providing heat map to the section where the kernel is expecting the person to be present the most. And based on that, segmentation can be performed and you will be ending up getting, some kind of a confidence or a prediction that the model is understanding that part correctly. But I have not done an extensive hands-on on the CV side, but maybe you can just check out Deep Lift, and I think you might be able to get the answer over there. And actually, if you go to the SHAP's documentation like GitHub, in that section at the bottom, you will be able to see that a lot of computer vision related explanations and examples are provided. So this is like the swarm, bee swarm charts are there, a lot of scatter plot charts are there, these force plots are there, different. And here, this is where the computer vision parts are there, where gradient explanations and all of those parts are provided. And then at the bottom, yeah, something like this. So this is where it highlights the area to recognize that particular entities. So this is like a classification again, but it provides that necessary heat map of positive contribution that says that yeah, this part of the pixel is more of a human rather than dog. And in that way, you will be able to get some more understanding of which one works best. So here you can go with the deep explainer. There is a notebook for sentiment classification is there. For kernel explainer, there is a ImageNet VGG model with Keras also. So you can go through this one. This might actually give you a better idea. So this would be something that you might find useful. So just explore this probably.
Sure. Yes. Can you, if possible, if we have time, can you also tell a bit more about Deep Lift? Like just a small bit about it.
No, I have not gone through deep lift actually. As I've mentioned, like I have not done enough on the
Yes.
computer vision. Yeah. So I have not done a hands-on on the deep lift side. So I have not been able to say anything at this point.
Sure. Thank you. Yes.
Yeah, Pavin, you can ask your question.
Yeah. Yeah. Hi, Tamoghna. Yeah, it's a nice presentation.
Yeah.
Quick question. So how can we make use of this SHAP for unsupervised models such as k-means or any other unsupervised learning models? So whether can we go with any it's a model agnostic methods to do this, or how it can be achieved? How can I complete, for example, if I have a customer segmentation or some problem, right? So
Mhm.
yeah, so how can I do it? I don't have any labels or something out there.
Okay, for unsupervised, right?
Yeah.
So the major problem with that unsupervised would be since you do not have the ground truth, so you will not be able to calculate the difference between the model expectation and the explanatory model output, right? So unless you have some levels of, I think you might have to start. I have not done this before, so maybe one thing that can be done, you can get a first iteration of the possible clusters that you can get, okay, and then on top of that you can labelize them and then see by performing explanation how well the like the how much is it deviating from the expected outcome probably, but I'm not sure.
Oh, okay. Okay.
I don't think SHAP with unclustered, I mean unsupervised, is exactly thoroughly present. So you might be able to check it out separately. I think there might be a different way, but yeah, mainly PCA and all of those things might be useful. However, in SHAP, it's saying that the kernel explainer should work with any kind of model, whether it is unsupervised or not. And in this section, only probably with that kernel explainer. But yeah, I think in the end, uh, I think you have to just read this part up. I have not explored this, but it
Okay.
might be
Yeah.
possible. Just getting that first round of predicted clusters, make them as the ground truth, and then start considering how much explainability can be done.
Okay. Okay. Thank you. Yeah.
Yeah. Can you please explain which part of the SHAP charts was for global explanations? Yeah, so actually this part at the end of, like, once you have the SHAP explainer, if you just straight away do a SHAP dot bar dot plot, here you can see I'm passing actually each and every instances, so the index number and the corresponding column name. Whereas here, once we do a SHAP dot plots dot bar, we're just passing all the SHAP values, that is the expected outcome, all the Shapley values for all the variables, and this is like the average Shapley value for RAD, average Shapley value for tax, average Shapley value for LSTAT, and this is what we get as the global explanation for that model. So here, the two most important features according to linear regression model is RAD, index of accessibility to radial highways, and tax, full value property tax rate per 10,000. So according to this linear regression model that we have trained, this is what has the most importance and impact. So that is how you can do it.
All right. Do we have any other question?
Just one more question. Can you please explain the partial correspondence plot, right? About that?
Dependence,
Yes,
partial dependency plot.
yes, yes.
Yeah.
Dependency.
So partial dependency plot basically is so just think of it like calculating the SHAP value for all the instances of the record CRM. Like CR crime rate. Okay, so crime is the value for you, right? So whatever be the Shapley value that you're going to calculate and the distributions of those record in this part, this is what you will be basically getting it as a partial dependency plot. So for all the rows for this column crime rate, whatever the Shapley values you're going to get, this is how somewhat the distributions of that record will look like. Okay, and you can also go to this uh, SHAP documentation. SHAP uh, over here, if you go to this section, topical overviews, here you will be able to see a lot more explanation on the partial dependency plot. So they have also used that same information and topic, and here you can also see how well they are talking about the partial dependency plot. So how do we read SHAP values from a partial dependency plot? It's nothing. It's as simple as just telling you that you have the expected base value of the model, you have the expected value corresponding to that particular column that you are considering, and this expected value is across all the columns, right? So wherever is that intersection happening, that is basically with respect to those SHAP values that you're going to generate. That is what basically you get as a SHAP value. So this is what you can see, the scatter plot that you perform of SHAP values corresponding to those RM column. If you plot it exactly all those SHAP values, it's basically forming that same line. So that is what basically the partial dependence plot is. So the distribution of this RM across the distribution of this RM column, whatever the corresponding Shapley value coefficients you get, that basically forms the partial dependency plot for you. So just for visual purpose or visual instance only, you are going to get this vertical line that says that this is the SHAP value of this column for this particular instance of record, like 20th row, 50th row, 100th row, etc. That's all. That is what partial dependency plot is. Just
Great,
read up
great.
just
Makes
read
sense.
up this place, and here you will also see the topic about fairness and biasness, how can it be avoided, and what you should be considering when you're going to talk about these informations, because sometimes if it becomes like a marketing customer segmentation, as Praveen was talking, so unless we are absolutely sure, if we bombard wrong advertisements to different people, this biasness might be playing a negative role, and you might be ending up getting a backslash out of it, right? So you must be very careful about the types of scenarios that you might be considering, where a biasness for women's income, biasness for underreporting bias for women's late payment, underreporting bias for women's rate. All of these are very important insights that can eventually get you to make an understanding that where and how can you improve the model at the end of the day. So is there any change you have to do from a data centric point of view, or is it something like a model centric where you have to fine tune some parameters even more? And even after fine tuning, if you notice that you're getting somewhat similar explanations, then it boils down to the data. So then in the data, you will be able to justify that, okay, this kind of biasness is basically contributing this kind of information bias towards the final outcome of the model. So you must take this into account while providing the necessary recommendations to the customer or the solution, whatever you have to do. Then whatever the business call is, whatever the final business call will be, you will have to take that call. Read this part. It's very, very good. It has a lot of information and lot of clarity. Okay. Any other question?
Yeah, Deepak.
Hey, Tamoghna, it's really a nice presentation, and
Yeah.
just want to know one thing. Can you suggest any method to do causation analysis, or I mean, what is the way to do that?
Positional analysis as in?
You mentioned right, so correlation doesn't imply causation. So this SAP values will just give that okay, these features were important or some correlation, but that doesn't imply the actual causation that this feature has caused these values
Oh,
or
you're saying causation. I actually misheard you. Sorry. Causation. Right. Huh. Okay.
yeah.
So
So
you, yeah, if you also actually check this part only, this is that subscriber retention example that I was talking about. So just
mhm.
check this part where this Microsoft people have actually explained that what kind of causal insights are you supposed to be careful of when you are considering any kind of business model or the policy choices that you're going to do that can give you some kind of any misleading information and get some results at the end of the day. So they're just creating some random variables over here, and I think they have some error in the way they are showing the plots over here. But mainly in this section is where they are actually talking about how um, customer retention can be having a totally different information compared to what the SHAP is providing. So this might be able to tell you that higher bug reporters are more likely to stick to that particular product, and thereby they are the most loyal, and hence they will be more having a high chance of retention. So you can check this part out. I do not have any other examples ready with my hand, but this might be a good starting point. So this is actually very good descriptions of what kind of causal insights, like a network graph it provides you, that tells you that okay, these features are directly impacting a feature X, ABC is impacting feature G, something like this is what it's kind of providing an information over here. I have not been able to successfully go through it completely, but this is where you can probably start off to see the kind of causal inferences that you can probably do. You just need to read up and make some changes in the values and over here, and then try out different scenarios to get a better understanding. But yeah, I think this can be a good starting point for you. It's everything in the
Thank
SHAP documentation. Just go through this. Case studies session on SHAP. That's difficult. It's going to be some time consuming, but we can definitely try something. Um, you can take up some Kaggle competition data sets, and take up probably Titanic data set and think of SHAP sessions. So maybe next time something that we can do, we can make this kind of like a interactive sessions where the kind of SHAP informations or insights that we have got, we might be able to exchange with each other, and then we can definitely see what conclusions each of us have derived on. Maybe that we can do. What do you think, Vijay?
Yeah, we can plan it. Maybe once you get some time to prepare.
Yeah, sure. Yeah, we can definitely try that part. It will be a very good session. It won't be like a one-way session. We can have interactive sessions.
Nice.
I have one last question from my side. It's
Yeah.
about the practicality of the explainable models, right? I have used Lime and SHAP previously
Mhm.
last year, And what happens is, I think SHAP takes more time compared to Lime.
Correct. Yeah, yeah.
So it's like, so how practical is it, like when running on like real world data, which can go up to hundreds of thousands to millions?
Yeah, that is where the trade-off is happening, right? So that's where I told you that if you end up using any model specific, like you have narrowed down to saying that, yeah, tree-based records are much more reliable, then just stick to that part and make use of it. Then tree shape would be useful, linear shape would be useful. In this way and that, you can definitely make some changes, you can tweak something, and then finally probably get some insights. But I will definitely suggest not to go with the entire data set. If it's like millions of rows, always take subsamples and try to stratify those records in a proper fashion and way. And then you will be able to get more insights and understanding that, yeah, this makes sense um, to some extent.
So does it mean like if the SHAP, just because SHAP is taking more time, does it mean that it is better than all its alternatives like Lime?
It might be, as I was mentioning, like the way we are selecting these background data sets, right? So this background data set choice and the sampling of those record will also provide some kind of impact for us. We end up getting selecting the first 100 rows, otherwise instead of maybe like the next 10,000 and one rows, okay, like from 10,000 to the 10,100 rows. So the fluctuations in that output will totally be dependent on this kind of sample that we select. And the bigger the sample we select, the more time it will definitely take also for the model to get some insights. So there will be some kind of partial dependency on the in terms of the data set that we are going to use or the seed that we're going to set up on, and we might be experiencing slightly different results. However, the way SHAP has been built is to handle those levels of deviations to the maximum possible extent, which I don't think is being successfully being implemented by Line. So practicality wise, it ultimately depends. Like you take a decision, you implemented it. If you see a positive outcome out of it, then that's it. Otherwise, it's not. Then go back again and see what mistake you made, and then try to redo it. So it's ultimately going to be, unless you implement it in the real world, you're not going to get any idea of it.
Yeah, thank you so much, Tamoghna. If you have any questions, we can have a discussion. If not, I think we can close. We are on time.
Yeah.